welcome back. We're now up to 2.6. In section 2.6, we will cover rational functions and their graphs. We will also cover in this section, we will determine the domain of rational functions. We will identify vertical asymptotes, identify horizontal asymptotes. We will also graph rational functions, and we will finally determine slant asymptotes. Now let's consider the example where we have to find the domain of each of the given functions. Each function is a rational function, and we know that in a rational function, we're very concerned that we are not dividing by 0. So we need to determine where the denominator is equal to 0. So x minus 5 is equal to 0 when x is equal to 5. So therefore, the domain of f is going to be the set of all x such that x is not equal to 5. This is set builder notation. We can also use interval notation to describe the domain of f. So in interval notation, the domain would be the set of all numbers less than 5, or the set of all numbers greater than 5. In the next example, B, we have the rational function g of x is equal to x divided by x squared minus 1. So again, we want to know when we are dividing by 0. So let's find out when x squared minus 25 is equal to 0. So we have x. So x is equal to negative 5, x is equal to 5. So the denominator x squared minus 25 would be 0 when x is negative 5 or when x is 5. So therefore, we must exclude a negative 5 and 5 from the domain of G. So the domain of G would be the set of all real numbers x such that x is not equal to negative 5 and x is not equal to 5. Using interval notation, we can also represent the domain as the set of all real numbers less than a negative 5 union from negative 5 to 5 union all numbers greater than 5. All right, so this is the domain expressed in what we call interval notation. In the last example, again, given the rational function h of x, x plus 5 divided by x squared plus 25, again, we're concerned where the denominator x squared plus 25 would be 0. And as we Observe x squared plus 25 cannot be 0. It can never equal to 0. So therefore, the domain of H just be all real numbers. Or we can express this as minus infinity to infinity. Now, let's consider the reciprocal function, which is defined as f of x is equal to 1 over x. And since it is a rational function, we clearly see that the domain is going to be the set of all real numbers x, except when x is equal to 0. All right, so that would describe the domain of this reciprocal function. All right, what would the graph of this reciprocal function look like? So the graph, if we were to graph this, all right, this would be the graph. If you want to check it, you can set up a table of xy values. Okay, let's now investigate some of the characteristics of this reciprocal function. It appears that as x approaches 0 from the left, so if x approaches 0 from the left, what happens to the value of the function? Well, as x approaches 0 from the left, the values of the function values tend to be what? Decreasing. The values are decreasing without bound. How do we write this? How do we symbolically represent that? So we say that as x approach 0 from the left. This is read 0 from the left. It's approaching 0 from the left. All right, as x approaches 0 from the left, we said that the values of the function are decreasing. So f of x is approaching a negative infinity. And symbolically, this is how we expressed the behavior. Now, let's consider what happens as x approaches 0 from the right. As x approaches 0 from the right, we see that the function is increasing. The values of f are increasing without bound. So what we write is that as x approaches 0 from the right, f of x is increasing without bound. So we say f of x is approaching infinity. All right. One more observation. As x increases or decreases without bound, so let's say that as x increases, what happens to the value of f of x? And as x decreases, what is the behavior of the values of the function f of x? All right, we see that in both cases, the values of f of x are getting closer and closer to the x-axis. In other words, they are approaching the line y is equal to 0, which represents the x-axis. Let's see how we would indicate this symbolically. So, as x increases without bound, we say x is approaching infinity. All right, so x is increasing. X is increasing. We note that as x increases without bound, the values of the function are getting closer and closer to the x-axis. So f of x is approaching 0. And likewise, as x is decreasing without bound, again, we note that the values of the function f of x are getting closer and closer to the x-axis. So in other words, f of x is approaching 0. So we conclude then that as x approaches infinity, or as x approaches a negative infinity, the function values f of x are approaching 0. So, in the first graph, if we notice what happens to the function as x approaches a from the right. So, as x approaches a from the right, we see that the values of the function f of x are increasing without bound. So as x approaches a from the right, f of x is increasing without bound. We write f of x is approaching infinity. In the next graph, we see that as x approaches a from the left, so as x approaches the number a from the left, the values of the function f of x are again increasing without bound. In the next diagram, the next graph, as x approaches a from the right in this diagram, so let's see what happens. As x approaches a, the line x is equal to a. As x approaches a from the right, the values of the function f of x are what? They're decreasing. They're decreasing without bound. So we write that f of x is approaching a negative infinity. In the last graph, we see that as x approaches a from the left, so the values of x are approaching a, the line x is equal to a from the left. As x approaches a from the left, we see that the values of the function f of x are what? Are decreasing without bound. So we say that f of x is approaching a negative infinity. we conclude here? So therefore, as x approaches A from either the left or the right, f of x approached in positive infinity or f of x approached a negative infinity. And when this occurs, the line x is equal to A is what we call a vertical asymptote. Now, in the next example, we will actually locate the vertical asymptote. So we're going to find the vertical asymptote of each of the graph of each of the rational functions. In part A, the rational function f of x is equal to x squared minus 1. So again, we're concerned when we're dividing by 0. So we see that, so f of x is equal to x divided by x plus 1 times x minus 1. If we factor the denominator, we have x divided by x plus 1 times x minus 1. And we see that x plus 1 is equal to 0 when x is equal to negative 1. X minus 1 is equal to 0 when x is 1. So, the denominator will be 0 when x is negative 1 and when x is equal to 1. Therefore, we say that the lines x is equal to minus 1 and x is equal to 1 are the vertical asymptotes. In the next example, example B, we have the rational function g of x is equal to x minus 1 divided by x squared minus 1. All right, so that's first very important to make sure that your rational function is in its simplest form. So let's see. X minus 1 divided by x squared minus 1. X squared minus 1 can be factored as x plus 1 times x minus 1. And if I simplify, I get g of x is equal to 1 over x plus 1. So by looking at the denominator x plus 1, we see that x plus 1 is equal to 0 when x is equal to negative 1. So therefore, we say that the line x is equal to minus 1 is the vertical asymptote. In the last example, the rational function h of x is defined as x minus 1 divided by x squared plus 1. As we look at and investigate the denominator, we see that x squared plus 1 is never equal to 0. So x squared plus 1 is never equal to 0. So therefore, there is no vertical asymptote for the graph of h of x. Now, let's look at the definition of a horizontal asymptote. All right, so if we have a graph, all right, and let's say that this is the line y is equal to b, and this is the graph, say, of our function. All right, so what we have here, as x increases, f of x, the values of the function tend to get closer and closer to the line y is equal to b. All right, so the line y is equal to b is a horizontal asymptote of the graph of a function if f of x approaches b as x increases or decreases. Another example might be, let's see, here's our line, let's say y is equal to b, and then we may have something like this. All right, so again, as x increases f of x, the values of the function f of x will approach the line y is equal to b, and this should have been b as well over here. So it's approaching, and you can see that as x increases, the values of the function are approaching the line y is equal to b. Now let's look at an example of actually how we locate horizontal asymptotes. All right, so let's say if we have a rational function where the degree say the degree of the numerator is n, and the degree of the denominator is m. So we have a rational function p over q divided by q over x. The degree of the polynomial in the numerator is n, and the degree of the denominator, the degree of the polynomial function in the denominator is m. So these are the conditions. All right, if n is less than m, the degree of the numerator is less than the degree of the denominator, then we say that the x-axis, or y is equal to 0, is the horizontal asymptote of the graph. All right. On the other hand, let's say that if n is equal to m, the degree of the numerator is the same as the degree of the polynomial function in the denominator, then we say the line y is equal to the leading coefficient in the numerator divided by the leading coefficient in the denominator is the horizontal asymptote of the graph. And if n is greater than m, the degree of the polynomial function in the numerator is greater than the degree of the polynomial function in the denominator, then we say that the graph of the function f has no horizontal asymptote. So let's see how these conditions apply in each of our examples here. So in the first example, we have the function f of x is equal to 9x squared over 3x squared plus 1. All right, so what do we have here? The degree of the function in the numerator, n is equal to 2. M is also 2, the degree of the polynomial function in the denominator. So therefore, n is equal to m. So we conclude that the line y is equal to the leading coefficient in the numerator is 9 divided by the leading coefficient in the denominator, which is 3. So the line y is equal to 3 is the horizontal asymptote. All right. In example 2, g of x is defined to be 9x divided by 3x squared. We see that the degree of the numerator is 1. The degree of the polynomial function in the denominator is 2. So n, in this case, is less than m. So if n is less than m, we conclude that the line y is equal to 0 is the horizontal asymptote in this case. All right. In the last example, h of x is defined to be 9x cubed divided by 3x squared. In this case, n, the degree of the numerator, is 3. The degree of the polynomial function in the denominator is 2. So what do we have here? We have that n is greater than m. All right, n is greater than m. So therefore, the graph of the function h has no horizontal asymptote. All right, in this example, we are given a rational function and we want to graph this rational function. The function is f of x is equal to 2x squared divided by x squared minus 9. All right, in order to graph this, we're going to go through the necessary steps to determine the symmetry, the intercepts, the asymptotes, and then putting all of this information together, we will be able to obtain the graph of this rational function. So let's first test for symmetry. All right, let's see. F of minus x is equal to 2 times a minus x squared divided by a minus x squared minus 9, which is 2x squared divided by x squared minus 9, which is the same as f of x. So we conclude that f of minus x is equal to f of x. So therefore, this is an even function, even In other words, it's symmetric about the y-axis. All right? All right, step 2. We need the intercepts. Let's find the y-intercept. All right, the y-intercept, so we want f of 0. All right, so f of 0 is going to be 2 times 0 divided by 0 minus 9. So we have 0 over a negative 9, which is 0. All right, so the y-intercept is the point 0, 9. All right, 3 x-intercepts. All right, let's see if there are x-intercepts. To find the x-intercept, we want the numerator, want to check 2x squared is equal to 0. So we get x squared is equal to 0, so x is equal to 0. All right, so we have an x-intercept at 0, 0. Okay. And now, let's check for the vertical asymptotes. In order to find the vertical asymptote, what do we want? Well, the vertical asymptote is when the polynomial function in the denominator is equal to 0. So x squared minus 9 is equal to 0 when x is equal to plus or minus the square root of 9, which is plus or minus 3. All right, so we have vertical asymptotes would be the lines x is equal to 3 and x is equal to minus 3. All right, now the horizontal, all right, the horizontal asymptotes. All right, so let's see here. In this problem, the degree of the polynomial function in the numerator is 2, and so is the degree of the polynomial function in the denominator. So m is equal to n, so therefore the horizontal asymptote is the line y is equal to 2 over 1, which is 2. So y is equal to 2 is the horizontal asymptote. All right. Now the only other thing we might want to do is to plot at least one point between the x-intercept and the vertical asymptote, or at least one point between, say, the x-intercept, well, not between, we've said between, and also beyond the x-intercept and the vertical asymptote. So let's choose a couple of points just for checkpoints, additional points on the graph. All right, so let's see. When x is equal to 1, so f of 1 is equal to a negative 1/4, so we're going to have the point 1, negative 1/4 on the graph. When x is equal to a negative 4, so we have f of a negative 4, which is approximately 4.5, so we have the point negative 4, 4.5 on the graph. F of a negative 1, but since we know this is symmetric about the y-axis, f of minus 1 is also here a negative 1/4, so we're going to have the point negative 1, negative 1/4, all right? And finally, let's say f of 4 Again, f of 4 is going to be 4.5, so we have the 0.4, 4.5. So we're going to use all of the information that we have gathered here to determine, or actually to obtain, the graph of that rational function. So let's see what we have. So let's see. Let's graph the function. Okay. So we know that the vertical asymptotes are the lines x is equal to -3 and the line x is equal to 3. We have a horizontal asymptote at 2. Y is equal to 2. All right? So this is the line y is equal to 2. What else do we know? Well, we have the x-intercept. The x-intercept is the point 0, 0. The y-intercept is going to be 0. It's going to be 0 as well. All right, and what else do we know? We have other points. F of 1. F of 1 is a -1/4, so about here. F of a -1 is also, f of a -1 is also a -1/4, so we have this. All right. So let's see what's happening here. So the graph is going to look like this. And we have other points. We have that f of 4 is 4.5. So this is 2, 3, 4. This is 3, so this is 4. So f of 4 is 4.5. 4.5 is about here. All right, and likewise, f of a -4 is also 4.5. So it's going to be here. All right, and so you can check more points if you like. So what we have, the graph is looking like this. And over here we have all right, so this is the graph of the rational function f of x is equal to 2x squared divided by x squared minus 9. It's perfect. All right, the next example introduces us to the slant asymptote. All right, so we want to find the slant asymptote of the given function. F of x is equal to 2x squared minus 5x plus 7 divided by x minus 2. Well, first of all, we note that the degree in the numerator is greater than the degree of the polynomial in the denominator. So when n is greater than m, what do we conclude? We concluded previously that the graph has no horizontal asymptote. All right. But it does have what we call an oblique or a slant asymptote. All right. So the graph, let me just repeat that. The graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the polynomial function in the denominator. All right, so let me speak. In general, all right, given, say, a rational function, f of x is equal to p of x divided by q of x, all right, to find the slant asymptote, we actually divide the polynomial function in the denominator into the polynomial function in the numerator. So when that happens, we have p over x divided by the polynomial function in the denominator is going to be mx plus b plus the remainder divided by q of x. Okay, so let's do that in this case. All right, so we have 2x squared minus 5x plus 7 divided by x minus 2. So that's x minus 2 divided into 2x squared minus 5x plus 7. All right, so we have x divided into 2x squared is 2x. 2x times x is 2x squared. 2x times a minus 2 is a negative 4x. All right, and now we subtract by changing the signs here. Minus 2x plus 2x squared is 0. A positive 4x minus 5x is a negative 1x. And now bring down the next term, which is 7. And we see that x divided into a negative x is a negative 1. 1 times x is a negative x, and 1 times a negative 2 is a positive 2. Draw your line, subtract. These cancel. So we have a negative 2 plus 7 is 5. All right, so therefore, the line y is equal to 2x minus 1 is the slant asymptote.